This series is also an opportunity to reconnect the department with former members of our community and to highlight that the CEGE department can serve as a resource to you after graduation. It's my pleasure to introduce Dr. Jordan Clark, who is an interdisciplinary expert in sustainable building systems within our department. He also holds an appointment as a core faculty member in the Sustainability Institute, and he has a partial appointment in the Food, Agricultural, and Biological Engineering department. I will share one quick highlight that Dr. Clark is the technical lead on a large Connected Communities grant from the Department of Energy, which will be using the Ohio State campus system as a testbed for controls to optimize energy use and efficiencies in urban building systems. I do ask that you please drop questions in the chat function at any time during the presentation. I will moderate those during the question and answer session at the end of Dr. Clark's presentation. And let us now welcome Dr. Clark.
Thanks, Allison. Share my screen. I think, Kevin, you might have to enable the sharing. Good deal. So welcome. Thanks for the introduction, Allison. That takes care of my responsibilities on this slide. I was going to introduce myself. As Allison said, I have multiple appointments throughout the College of Engineering. My primary home is in civil engineering. I do some things that are probably not thought of as traditional civil engineering. I work on sustainable buildings, specifically on heating, ventilation, and air conditioning technology. And then a lot of my research and a lot of the research of a lot of people in the energy world has kind of moved into interfacing their research with what's going on with the electrical grid. And I'm going to talk a lot about that today. A little bit more background. Originally, I did my PhD at the University of Texas at Austin, and then I did a couple postdocs, one at the National Renewable Energy Lab and one at Lawrence Berkeley Lab, but I am a native Ohioan. I've been rooting for the Buckeyes since a very young age, so go Bucks. So today, Allison asked me to talk about what's going on in the future. So I wanted to talk about buildings and their role in the future, but the biggest change in how buildings are going to operate has to do with how they interact with the grid. So I'm going to end up talking a lot about the power grid and what the grid of the future looks like, and then some challenges and opportunities that that's going to present, and then what kind of roles smart buildings can have in answering those challenges. And then I'll go through two case studies that kind of demonstrate the importance of that role in the future grid. So whenever we're going to talk about the future, it's often beneficial to kind of take stock of where we are now and then where we're going. So we'll do that. So you guys have probably seen this graph before. This is a graph of the global average temperature for the last 70 years. And we can see that before the Industrial Revolution, we were kind of hanging out at a pretty constant place. And then Industrial Revolution starts beginning in the 1900s. This is given in the deviation in degrees Celsius from the average between 1850 and 1900. And we've been constantly climbing as a planet since then. No signs of slowing down, except, in fact, we might be picking up a little bit. So as far as the temperature of the planet, that's kind of the solution. By the way, I expect this to flatten the curve because of the actions of a lot of engineers, and we'll get there eventually. But right now, we can't see that too clearly. And we think this has something to do with it. This is the atmospheric carbon concentrations over the last 10,000 years. And again, we're kind of hanging out in a pretty steady place. Beginning of the Industrial Revolution, we have this exponential growth, and here we are today, which is kind of causing what we were looking at on the previous graph. And that has to do with, of course, the way we power our economy, the way we've improved our lifestyle and our quality of life over the last 100 years has a lot to do with the energy that we're using to power that transition. The vast majority of this, of course, has come from fossil fuels, shown in blue here. We have a little bit coming from nuclear and a small portion of our energy budget coming from renewable sources, but that portion is growing, and it's poised to grow quite a bit in the near future. So where is specifically our electricity? Where is all this power that we're generating coming from, and where is it going? So this is a cool little mesmerizing graph that they update every 5 or so years, showing all the sources of energy, not just electricity, over here, and then the ultimate end uses over here. A couple things to notice. First of all, we're going to be talking mainly about the electric grid today, so we're focusing on this portion. You can see that about all this gray chunk here, this is rejected energy. So this is about 2/3 of all the electricity that we produce in our power plants is going to be wasted. First time I found out about that, that was pretty heartbreaking. Work hard to make this electricity, and then 2/3 of it gets dissipated basically as heat. About 1/3 of it gets lost at the site. We basically, the way we generate power these days is we light something on fire and then we turn a turbine. So about 1/3 of that energy goes through the stack in the form of heat, and then about another 1/3 is lost in the transmission and distribution. And by the time an electron gets to your house so you can watch TV, that electron was responsible for about 3 electrons that were generated at the power plant. So that's the first thing to notice. And then the second thing to notice is that about 75% of the electricity generated today is used in our building sector, in our residential and commercial buildings. So if we're talking about the demand for electricity right now, we're talking mainly about buildings. There's a little bit that goes to the industry, but the biggest chunk is from our buildings. Lastly, the transportation sector right now, obviously it's largely powered by liquid petroleum. That's changing quite a bit, and that'll play into the changing grid in the near future. The last thing I want to talk about as far as where we are now is the distribution of energy resources. So by that I mean how concentrated are the generators within our grid. So this is showing the PJM service territory. PJMs are local grid operator, kind of runs from New Jersey over to Chicago. The total capacity, generation capacity, within PJM service territory, about 185 gigawatts. That is created by about 1,000 different generators. So you guys can do the math. That means we have the average size of a generator, about 100 megawatts. That's actually quite big. We're building a 100 megawatt power plant on a high state campus. It's supposed to be operational next year, I think. It's a combined heat and power plant. So just to give you a sense of the scale, a 100 megawatt power plant can power a campus of 100,000 people or so. So the point of this is that it's quite concentrated. We have a few big power plants dotted across the territory, and that's also poised to change, and I'll talk about that a little bit. So where are we going? Lots of big changes on the horizon. So this is the additional additions to U.S. power generation capacity in 2021. And in the coming years, looks quite a bit like this, maybe even more slanted toward the renewables. So you can see all these yellow dots. These are solar installations. The green dots are wind farms, and then the few blue dots here are natural gas fired power plants. And then we have a big nuclear facility in Georgia here. So this is the point of this is we're dominated by solar installations and by wind, right? So even though currently the overwhelming portion of our electricity is coming from fossil fuel sources, in the near future that's going to be changing quite quickly. We can zoom in on that a little bit. Again, the PJM service territory here. This is showing planned retirements and planned additions in capacity, and the fuel that they use. So these big boxes, the gray boxes, these are coal-fired power plants that are getting retired. All this is solar installation, these yellow dots, and then up in the northwestern corner of the state, a little bit in Indiana, are the wind farms. We do have a few natural gas plants still being built. And I should say on top of this that our area is one of the worst places in the country to do renewable energy. That's just the way it is. The sun shines less here than anywhere but the Pacific Northwest, and other than the northwest corner of the state, we have a very small wind resource here as well. So the economics of solar and wind are about as bad here as they get in the country, and yet the vast majority of the planned capacity is going to be in a renewable form. So if we can do it here, we can kind of do it anywhere. And in fact, they are definitely doing it throughout the country. So just to put a point on that, currently, yeah, less than 2% of PJM's capacity is renewable, but in the queue to be added, 73% is solar and an additional 10% wind. So we're almost not renewable at all right now, but we're moving to completely renewable power grid. Okay, another big change is how we power our cars, of course. So both of these graphs are showing different entities' projections of electric vehicle adoption. And the big takeaway from this is that every year, every entity is revising their projections upward. This is happening a lot more quickly than we thought it was going to happen. What do I want to say about this? A couple different things. It's happening more quickly. This is actually, from what I understand, it's been slowed down by the pandemic and the shortage in global shortage in chips. So a lot more people want EVs now than can even get them, and we can expect this to accelerate even more. So that's going to be a big change to where our electricity is going as well. So this is back to the original diagram. These are the kind of changes that we can expect in the near future. Obviously, solar and wind are going to play a much bigger role. We can expect that the coal-fired power plants and the liquid petroleum that we're putting in our cars are probably going to go the way of the buffalo. We're going to have to get that energy somewhere else, which means we're probably going to have a big addition in demand for electricity from our transportation sector. In fact, we're expecting more than a doubling of demand on the power grid, so a big shakeup there. And then in addition to that, hopefully because we're generating electricity in a little bit more efficient way, we can reduce some of that rejected energy. We're no longer setting things on fire to generate power, so we should be able to capture more of what we create. And then the last thing is that there's a big push to electrify all loads within our buildings. So instead of gas-fired furnaces and gas-fired water heaters, there's going to be a lot of incentivization to do heat pumps, which is electrically driven technologies. So that'll be an additional electrical load that goes onto our grid. Big changes. On top of all that, in 2020, FERC, this is the Federal Energy Regulatory Commission, passed this order 2222. What this basically says is that small players are now, the grid operators are required to make a plan to allow for these small players to add energy at wholesale prices to the grid. So by small, we mean an energy resource of 100 kilowatts or more. So to give you a sense of scale, if we had maybe 100 homes on a sunny day, they might be able to create 100 kilowatts on their roof, or 100 homes that are like turning off their air conditioning at the same time, that might be able to provide a 100 kilowatt resource. So this is in contrast to what we saw before, where the typical player, typical producer of energy was about 100 megawatts, so a factor of 1,000 smaller. So in addition to this big change of having a much more renewable grid, much more demand on the grid, two or more times, we're going to have a much more distributed grid. So a lot of different producers, a lot of distributed storage, and then a lot of aggregation of this load shedding, which I'm going to talk a decent bit about in a second. So big changes on the horizon. So what does this mean for the grid, and how can buildings play a role here? I think we said that we expect the climate, at least in the near future, to be more extreme. No signs of it slowing down yet. We expect our fuel mix to be more renewable. The big difference between renewable sources and fossil fuel fired sources is that the sun kind of shines what it wants to, instead of having the power plant kind of at our disposal how much it produces. So we're going to have to work around the the variation in supply, and maybe do something on the demand side to meet that kind of variable supply. Our electricity demand is poised to go up at least 2 times when we add in the transportation sector. And then the concentration of the energy resources is expected to be much more distributed than it is now. So we can lump that together and say our supply is going to be a lot more variable, and it's going to be a bit less predictable. Okay, so here's one kind of illustration of what that means for us and kind of the challenges that this is going to present. This is called the duck curve. If you kind of squint a little bit, you can see a duck here, right? It's got some wings that are drooping ever more every year, and then a little head of the duck, and put a little beak on it just to highlight that. The duck curve, so this is kind of a exaggeration. This is a little bit of a caricature. This is real data, but this happened in California, for one thing, where the sun's always shining, and it happened on a spring day. So you can think like spring day, so not a lot of demand for air conditioning, and at the same time, there's a decent amount of sun outside, so we have a lot of solar production, but not a lot of demand. So that kind of exaggerates what I'm going to talk about right now. So ideally, if we're running a fossil fuel fired power plant, the best kind of demand profile would be a flat line like this, and we could just operate at the same speed, the same number of plants the whole time. We wouldn't have to be turning things on and off. So that would be ideal, something lower than it is now and constant. Obviously, that's far from what we have here. What we have here, this is the net demand. So if you take the demand of all the consumers on the grid and then subtract out the renewable production, mainly from solar when the sun is up, you get a profile that we're seeing right here. So what's happening is, nighttime, not a lot of electricity, people start to wake up, and then if there were no sun, the demand profile would continue to grow like this, and we'd have a peak here late afternoon when everybody's kind of coming home from work and starting to cook, and all the retail and the office buildings are still running full blast, and we get a peak about 5 or 6 at night. When we add solar production to that, we get, in the middle of the day when the sun's shining, we get more and more solar production, and that drives this down to here. And as we add more solar to the grid, this goes even lower. And what results is a couple things that are not good from the grid's perspective. One is that this peak, despite adding more solar, we're doing nothing to lower that peak. So this peak determines the capacity. It determines, especially if this is like the worst day of the year, it determines the overall capacity we need on the grid. It determines, how big the wires need to be and things like that. That's one problem. Another problem is this increased ramp. So as you can imagine, if you've ever had a big piece of equipment, these things aren't easy to turn on and off. A power plant even more so. So ramping up is a challenge. Ideally, we would like a gradual ramp up, but this keeps getting steeper as we're adding more solar. And then the third thing is that we have to maintain a base load. So the base load is what's produced by those kind of clunky power plants, the ones that can't be turned on and off very easily. And we tend to run those at a constant speed, constant output. If we drop below that base load, that means this is kind of energy that we can't use, right? So we have to have what we call curtailment, which is renewable energy that we worked hard to produce that we can't use. So far from the flat profile that we would like, we have this wide variation, oscillation in net demand. What this kind of means is that we need a lot of flexibility, both on the supply side and the demand side, some way to kind of bring this belly or the wing of the duck up and maybe move the head down. So we need some flexibility, and that's the main thing we're going to talk about in the next few slides. So where does this flexibility come from? We could get the flexibility from either our supply side, meaning our power plants and the transmission and distribution grid, or we get it from the demand side, which is mainly right now our buildings. On the supply side, we could do things like fuel switching if we have both the ability to produce electricity with natural gas and with solar. There may be some opportunities there. Grid level storage in the form of batteries that exist in a few places. That's still quite expensive. And then there are some emergency generators. The grid operator will contract with a lot of different emergency generators to fire those up in cases of emergencies. On the demand side, we can have distributed energy storage in the form of, for example, thermal storage. Thermal storage is a little bit easier to do than battery storage, a little bit cheaper. So we could do something like create ice when we have abundant electricity, run the compressors then that are needed to make that ice, and then kind of run air over the ice that we'd created before to make cold air instead of running our air conditioner later in the day when the power was more scarce. So that's one thing. Distributed battery storage in the form of Tesla walls in people's garage, or a lot of different ways that could shake out distributed batteries. These are still quite expensive. Much less expensive is things like changing the scheduling of our heating, ventilation, and air conditioning systems. So my group and plenty of other people have done a lot of work looking at how do we modulate our HVAC systems in order to play nicely with the grid. And I'll give a few examples of that in a second. Appliance scheduling, so like running your dishwasher in the morning when power is abundant, and maybe turning it off in the late afternoon when it's scarce. Shifting occupant behavior, so that might be kind of what we talked about in the use of appliances, or things like changing set points, or changing when you cooking in the morning, things like that. And then some of our HVAC systems have variable capacity, so variable speed compressors and fans and things like that we can modulate downward during these times of peak demand. So these are some examples of how we can provide some of that flexibility with our buildings. I'll go a little bit deeper into some of these. So providing flexibility through occupant behavior, a lot of utilities, especially on the West Coast, are trying to incentivize behavior through this time-dependent rate for electricity. So in case you're wondering, at least where I live, I'm paying about this much all the time, and it's perfectly flat, about 10 cents per kilowatt hour. Different utilities are trying out different pricing structures. So if we have abundant energy in the morning and early afternoon, maybe the price is a little bit lower, and then during these peak times, the price is a little bit higher, trying to move occupant behavior a little bit, and that's working to some degree, and still being worked out. There's a lot of different rate structures that are being tried out, and we can kind of expect that. Most residential customers in America don't pay time of use. That's what TOU means, time of use, or a variable rate. We usually pay a flat rate, but you can kind of expect that to come within the next decade for sure. It's great to rely on occupants to change their loads. That might be possible to some degree, but it would be even better if the building kind of did it for them. And our buildings are becoming much more intelligent, a lot more distributed sensing throughout our buildings. This Internet of Things will kind of tell the building what's going on within the building, but it also, our buildings are starting to have more knowledge of grid needs as well. A lot of our buildings are becoming grid tied, so they have some means of communication from the grid operator, ability to send a signal to the building and say, hey, we're kind of hurting right now. Can you kind of change your operation for a little bit? We're going to be doing some of that on the High State campus that we'll talk about later. So our buildings are getting smarter, so they know more, and they're also getting better as far as their ability to change things. So instead of just kind of constant scheduled HVAC set points, we may be able to modulate that, hopefully in a way that the occupants don't even know that that's happening, or at least in a way where the level of comfort is maintained to a certain degree. What else do I want to say about this? The one thing you might notice that this little bubble is not the same colors as the other bubble. That's because I stuck this on. This is the Department of Energy's conception of a grid interactive efficient building, this acronym GEB they're using. They didn't put smart indoor air quality control, but that's one of the kind of main focuses of my research. So I'm lobbying to get them to stick something like this on there. We'll get it eventually. Okay, so what does this look like exactly? So one thing we could do to provide some flexibility is to change the operation of like air conditioning systems and heating systems. Mainly we're talking about those summer peaks right now, so it's mainly air conditioning systems. This is happening at Ohio State campus, as we speak, a few times a year during those critical peaks, the grid peaks. Ohio State gets remunerated for shedding some of its load and reducing the ultimate capacity that the grid has to provide. So this is what this looks like. This is chilled water demand. This is really cooling demand. We're cooling our buildings with our chilled water system. Some kind of notice comes from the grid and says, could you please turn down your chilled water? And we have some contractual agreement with them. Prior to that, we turn up the set point a bit. So I think they're putting it at about 78 in most of the campus buildings during that time. And we see the load go down. This is a projection of what it would have been had that not happened. So the delta between those two is the shed. In aggregate, so this might not seem like a whole lot. This is about 10 kilowatts, but in aggregate, of course, the big customer like Ohio State, and then if we aggregate that with all the loads in the state or on the grid, that can end up being quite a big resource and can prevent the energy suppliers from having to build power plants that they only use a few hours a year to provide these peak loads. So it's cost effective for them, and then the end user benefits as well. So that's kind of thermal load shifting, load shedding. We've explored how we could do this with ventilation as well. So this is it's got a lot going on. I'll try to explain it real quick. The blue line is showing the outdoor temperature. It's basically nighttime, it gets cold. Daytime, it gets warm. Our ventilation energy required for the ventilation is proportional to the temperature. So it's really cold outside and we're bringing in a bunch of cold air for ventilation. We're going to have to heat that up. It's an energy intensive process. So if we're able to modulate our ventilation over the course of the day and maybe bring in some more ventilation air when it's nicer outside and maybe bring in a little bit less when it's not as nice outside, don't worry much about these black and red lines. These are some quantification of the airborne pollutants that we're exposed to. So all these strategies that we looked at had the constraint that we had to be, over the course of the day, be exposed to the same amount of airborne pollutants, even while we're modulating the ventilation. So if we can turn things down when it's advantageous to do so, and turn things up when it's advantageous to do so, we showed that this is TDV savings. This is time-dependent valuation. It's kind of like that graph we showed a few slides ago. This is closer to the real value of electricity. Again, we might be paying, especially in Ohio, a flat rate, but the wholesale price of electricity is fluctuating throughout the course of the day. So this is reflecting the true price or the time-dependent valuation. We showed that depending on climate zone, especially climate zone, this is all done in California for now. Climate zone 10 is quite hot, and these are different buildings within that climate, different types of building within that climate zone. But in the best ones, we can knock off something like 17%. This is annual TDV. So all of the real cost of electricity could be knocked off. 17% of that total for the year could be knocked off just by modulating ventilation during those peak times. So it's another way of adding that flexibility that's so needed for the new grid. And then this is just a slightly different control strategy where we're specifically trying to knock down peak power demand, and we got somewhere, I mean, the best performing things, we got greater than 20% of the peak demand knocked off. Did the same thing in offices. This is the exact same thing. We got a little bit less resource. And again, if our theory is right, this is all in modeling space. We're actually going to try this out in the real world next year. A little bit less resource, but something like 8 or 9 of the total, 8 or 9% of the total building load we could reduce during these peak events. Let's see. Another way of providing this is something that I worked on before even coming to Ohio State, like 2015, the postdoc at NREL. We looked at using like refrigerated display cases. We were in a Whole Foods and kind of using them as a thermal battery. So you can imagine that if we turn off your compressor to the refrigeration system, it's not like your frozen chicken breasts are immediately going to spoil or anything. There's some time constant associated with that. So we looked at how long we could turn these down or off for, and then what kind of ramifications that was going to have as far as how much we could actually shed as far as power demand. So it might look something like this. If we know that there's going to be a need for some load shedding at, let's say, 2. In this case, we had a period from about 2 to 8 where the grid operator wanted us to shed load. So we kind of overcooled a little bit and made all the product a little bit colder than it normally hung out at. And then turned things off. We really just turned up the set points so that the compressor never kicked on. And the temperature inside the case will rise a little bit during that, but it never hit the bound where it had to turn back on. And then the delta between, you know, the baseline of what it would have been and what we actually measured is the shed, which we're showing here. And in aggregate, we did this at a few different supermarkets, but if we kind of pooled that resource throughout, this is Bonneville Power Administration. This is Pacific Northwest grid operator, or local utility, actually. Within their service territory, if we pulled all these refrigerated display cases, and these are just freezers, and just the ones without ice cream, because they wouldn't let us take the chance of melting their ice cream. We said that those together acted as a 20 megawatt resource. So that's kind of equivalent to 20 megawatts. You could kind of run a small town with that, and that's just from the refrigerated display cases. So all these different ways people are looking at to provide this flexibility to the grid. People getting quite creative. And the kind of biggest project that I've worked on having to do with these topics is the project that Allison mentioned at the beginning of this. So Ohio State was just awarded this Connected Communities grant from the Department of Energy. This is a big $5 million grant over 5 years. We were the only university selected. Most of the awardees were private sector and utilities and NGOs. So we're kind of proud of that. And this is to show how we could do this at a campus level. So how we could move energy around in time, or power demand around in time, both to provide some energy efficiency within our campus and also to provide grid resources to the local distribution network, the AEP network, and then the bulk grid as well, run by PJM. So yeah, we're looking at 25 buildings. We have about 65,000 square feet of photovoltaic solar panels on campus. We have 29 electric vehicle charging stations, and I think that number has actually grown since I wrote this. I think it's quite a bit more than that, and it's growing. As I said, we're building this combined heat and power plant on West Campus, and then a big chiller plant beside it. And then we have this wind power purchase agreement with a wind farm in northwestern Ohio, and we may very well be getting some batteries on campus. We're trying to make that happen. So the objective of the project is to coordinate the activities of all these different distributed energy resources and all these buildings, and optimize their operation in such a way that we can save our energy on campus, reduce our carbon footprint, and also play nicely with the grid, as we were talking about before. So that's just getting started. Exciting project for the next 5 years at Ohio State. Okay, so I wanted to end the presentation by showing two case studies that kind of demonstrate the need for this flexibility and what happens when you have a lot of flexibility in your grid, and what happens when you have not so much. So the first case study we wanted to look at was this Texas cold snap that happened in 2021. You may remember they had record low temperatures in Texas. I actually lived in Austin for 4.5 years, and I think we had a dusting of snow one time, and everybody kind of freaked out, and dog freaked out. It's just not a very common occurrence down there. So record low temperatures, quite a bit of snow. This led to ultimately a 28 gigawatt shortfall in the supply of electricity. So to give you an idea, 28 gigawatts, that's you could run something like 10 Columbuses with that. That's quite a bit of power. And this is the shortfall, the difference between the demand and the supply. This led to 4.5 million homes being without power. At least 246 people were killed across 25 counties, and about $200 billion of property damage, all because of this power outage. Okay, so why did this happen? I'm taking all of this from this report from the University of Texas at Austin. As you might imagine, there's a lot of political finger pointing associated with this event. The renewable energy advocates are yelling at the fossil fuel guys in Texas, and the fossil fuel guys are pointing fingers at the renewable energy guys. I can kind of vouch for these guys because I know Josh Rhodes quite well. We had the same advisor in grad school, and man of integrity, so we can kind of trust these numbers. So this is showing total capacity, about 82 gigawatts for the entire grid. They had some routine. Okay, sorry, I'll back up a little bit. This is the projected numbers. This is what the grid operators projected as like the worst case scenario, the extreme peak with extreme outages. So this is the worst that they ever imagined would happen to the grid. Started out with the 82 gigawatt capacity. They assumed about 4 gigawatts would be out because of routine maintenance. About 10 gigawatts would be forced out because of the weather event. And then the maximum demand they ever expected was about 67 gigawatts here. That's under the coldest conditions that they had modeled. I should say that most of the heating done in Texas is with heat pumps, so it's done with electricity rather than with natural gas, like most of the heating in Ohio is done. So this is electrical load mainly for heating homes. And if all this happened, these are all the worst case scenarios they imagine, they would be left with about a gigawatt left over in the form of reserves. On the right is what actually happened. They started with the same capacity. Their wind farms actually produced a little bit less than they were expecting, that were projected, and that's not because they stopped working. That's just because they had less wind than they thought. It gets really cold. It's kind of stagnant outside. Their routine maintenance was about the same, not too different from what they expected. More than double the outages than they expected. So these are things that were forced off, the generators that were forced off. We'll talk about how that happens in a second. And then the big thing was that they had about 10 gigawatts more demand than they had planned for. That's primarily from bad weather forecasting, but perhaps also a little bit of the occupant behavior that they weren't quite expecting. So what ended up was this 28 gigawatt shortfall instead of the 1 gigawatt surplus, and then all the bad things that followed from that. So just a little bit of timeline, how this happened. They had some freezing wind turbines that were kind of the part of the beginning of this cascade. So again, we're changing to renewable energy. That presents a few challenges. They also had freezing cooling lines and some other things that took the fossil fuel generators offline. So we had a big drop in the supply side. Yeah, this is kind of the beginning of the event. The wind was leading the losses, showing losses in megawatts. So at the beginning, the wind was the big portion of the losses, and then the fossil fuels caught up, and they were also contributing to the shortfall. And then the shortfall in turn caused a decrease in frequency on the grid, and there's a bunch of equipment that has to match frequency. And if it goes a little bit out, we're usually at 60 hertz in America. If it goes a little bit out, a lot of generators as well as some of the load is going to have control logic in it to automatically shut it down so it doesn't damage it. So we had this cascading effect where we dropped and dropped and dropped, and that kind of led to the calamity. Also, fuel shortages. So not only was the electricity in short supply, but the natural gas that powered some of these generators was in short supply as well. So some of the backup generators couldn't turn on. And then finally, there is a kind of summer, what we call a demand response program in place. That's the kind of thing where they ask consumers to like turn up or down their air conditioners or heaters. This was activated to some degree during this event, but as far as this report talked about, it didn't really make much of a difference. It's not clear that it really any substantial amount of power was demand was reduced because of this program. So just a bunch of contributing factors, and kind of highlights again the need for this flexibility. We can contrast that a little bit with what just happened in California. By the way, I lived in California and in Texas. I'm not knocking Texas here. I like Texas a lot better than California, actually, but I think you'll see that California performed much better during their crisis than Texas did here. So again, we had extreme weather, as might be expected, and we should probably be seeing more of that. 114 degrees in Northern California. Again, a little personal anecdote. I lived in Northern California for 1 year, and because it's so ridiculously expensive there, I had a illegal Craigslist apartment, and it had no heating or cooling in the apartment, and that's just fine because Northern California is nice pretty much all year round. So I was like uncomfortable like 2 or 3 days that year. So 114 degrees is very unseasonable for Northern California. Extreme weather, they ended up with a peak demand of 52 gigawatts. So this exceeded their previous peak by about 2 gigawatts, so quite a bit. And yet there were no centrally mandated load sheds. Nobody lost their power. Their power was forced off. There were a few local utilities that shut things down temporarily, but there were no centrally mandated shutdowns. So quite a different outcome. Let's kind of look at why that happened. So this is different supply from different sources over the course of that critical day, September 6th. So we have natural gas here in this orange line, some solar obviously in the green line, and this is imported stuff that's brought in from a different grid essentially. The big difference from normal operation, first of all, this amount of natural gas is not obvious here, but switching to this natural gas may very well have saved them. This is way more than is used on a typical day. So they're able to fuel switch. They had some flexibility there and where they got their power from. So that's cool. They actually deployed 3 gigawatts of grid connected batteries. So this is on the supply side, not in people's homes or anything like this. This is on the grid side. Way more than most states or most grids actually have installed right now. So 3 gigawatts, quite a bit. So that's enough to power Columbus and all the suburbs during a quite hot day. So quite a bit of deployment of the batteries. And then one of the big differences was in the retail customer behavior. So California had this program in place, this Flex Alert, where they can kind of alert everyone that they're going through this event where power is scarce, and advise them to like turn up the air conditioning, set point a little bit. Here's all the things that everyone was advised to do. Things like cool your home down in the morning when power is abundant, and then turn things off at night when it's more scarce. Do some of your cooking and your washing and things like that in the morning again. Charging electric vehicles again in the morning and not in the late afternoon. Closing shades so your overall kind of thermal demand on your building is not as great. Things like this. This went out via text and Twitter and things like that to the retail customers, and then somewhere around I think 6 o'clock on that day, I believe this alert showed up on every single Californian's phones and said, "Come on, please turn things down. We're in an emergency here." And a lot of people are crediting this with saving them. And it's estimated. It's hard to crunch these numbers because you don't know what your baseline is. You don't know what would have happened necessarily if this hadn't happened. But the estimates that I've seen on the internet from reputable sources, about 1 to 2 gigawatts were shed just through the retail customer actions. So that's kind of amazing, especially considering the alternative, which is usually about 0. So cool. And what happened? So this line here is showing demand. This is the demand before what we're calling the demand response event, when all those calls went out to change behavior. And then the red line is showing during the demand response event, which lasted well into the evening. And then you can't see this real well, but this hatched part here is the supply. And we can see that we just barely, California just barely snuck under the point where they would have kind of run out of power and had some of those cascading failures that Texas saw. So should throw some big caveats in there. First of all, California, this was in the summertime, obviously, and the Texas example was in the wintertime, so these are quite different. One of the ways that they're different is that the cooling loads, the demand kind of matches the supply. If you have solar production, obviously the cooling demand is driven by the solar loads, and the additional solar is also jacking up the supply. Nothing of the sort with the heating loads, right? The wind doesn't blow harder when it's colder outside or anything like that. It should be noted that solar panel efficiency does drop off considerably with increase in temperature. So the solar resource did decrease during this event in California, and actually the order, that's what this graph is showing. Just trust me if you don't want to look at it for very long. But yeah, the decrease in the renewable production in California during this event was of the same order of magnitude as the decrease in wind production in Texas. So that wasn't really a big player. Californians are much more used to this dynamic pricing and to changing behavior because some of these time of use rates are already in place there. So the typical retail customers they don't think it's insane to be asked to do their laundry in the morning or something like that. Whereas in Texas, that may be a little bit different. And the larger part of the demand is in the form of electric vehicles. So you might imagine that people are a little bit more apt to charge their car during the nighttime and not at the peak time than they would be to turn down their air conditioner in the middle of a heat wave. So you might say that factored in, but really this is the latest numbers I could find from the California Energy Commission. And yeah, about 6% of electricity is going to the entire transportation sector. So that includes EVs and street lights and things like that. So it's not a huge fraction, but that is a difference between California and Texas. And of course, the other difference is that the barbecue is way better in Texas. So a little bit of caveats, but I think it's clear that California handled that crisis a little bit better. And the reason that one of the big reasons they were able to do that is because of the integration of all this flexibility beforehand in the form of batteries on the grid, flexibility in customer behavior, in-use retail customer behavior, flexibility in terms of what kind of fuel that they could use. So this kind of demonstrates the need for this flexibility and the consequences if it's not integrated. So main takeaways, yeah, the grid is changing. We're moving towards the more renewable grid, a more distributed grid in terms of where the energy is coming from. That leads to more variation. We'll have a more variable generation pattern, a less predictable one. And this needs to be met with more flexibility, both on the supply and the demand side. Our smart buildings are going to provide a lot of that flexibility. So you should be on the lookout in the future for smarter everything, smarter buildings, smart grid, smarter appliances, of course, smart heating and cooling, lights, etc. And then we'll probably see it later than a lot of the other parts of the country. But we can expect the role of the consumer, that's residential customers as well as commercial customers, to be a little bit different, a little bit more participatory. The first way that might come along is in opt-in programs, either opt-in for time of use rates or opt into different programs for being able to control your thermostat. I actually have that on my ecobee thermostat right now. I can opt in. I haven't done that yet because I don't know exactly what's behind that, but may eventually. So these are some of the big trends we should see in the near future, and I hope that was informative and you learned something. And happy to answer any questions.
Well, thank you very much, Jordan. I think we're a small enough group here that we can raise hands if folks have questions, or there's still an invitation if you'd like to drop them in the chat. I can maybe kick us off with a question. So there has been increasing discussion now, kind of in the context of engineers doing design on large projects, to not just be thinking about what the capital cost is when you start a new project, but also be thinking about the longer term operational costs that are imparted by certain design decisions that might be made early on. And I'm wondering if you could sort of speak to what you see as how your very detailed work may be merging together with that of civil engineers that are graduating from our program, and whether or not they may need to have some extra expertise as we're moving forward into the future.
Big question. So I'd say, for one thing, typically like electrical engineering or mechanical engineering, which is where this kind of stuff usually lived, the methods that they use and the way they think about problems, I think, is becoming less applicable to our electricity infrastructure. It's acting more like a piece of civil infrastructure rather than a self-contained, isolated system that you could analyze with methods of mechanical engineering and electrical engineering. So several of us are kind of trying to claim the power generation and distribution infrastructure as something in the civil engineering realm. Whether we'll be successful in that or not is yet to be seen. So yeah, and this is going to interface with a lot of different aspects of just the engineering of our societies, whether it's our transportation network. Obviously, if we're having to provide power to move the cars and buses and everything else, it's quite a different situation than if we're individuals filling up the gas station. We also have, I thought at the beginning of your question you were moving towards like thinking about decisions about where does power go, and there's going to have to be some kind of civic responsibility for making those decisions, and a lot of people are talking about that. In fact, Daniel Gingrich and Phil Ramsey, who I saw earlier, are thinking about that deeply with me about how do we, if we're going to optimize the operation of our community, let's say at a community level, we're going to have to make some decisions about who gets power and who doesn't, and things like that. How do we make that decision in a fair way and things like that? So, yeah, civil engineering is growing, and the definition is going to get a little broader for the challenges we're facing.
There is a question in the chat. Oh, there's a couple of questions in the chat. One that a comment that the OSU facilities department has 3D models of most buildings on campus. And the query is to whether you're planning to leverage any of that information in the project grant you spoke of.
Oh yeah, OSU facilities has been extremely helpful. We've got all those Revit models, 3D models you're referring to, and then as well as access to all the building automation systems and construction drawings and things like that. They've been nothing but extremely helpful. Been great to work with. I just got a tour of the steam tunnel network at Ohio State this morning. That's a really cool place, especially at 8 a.m. So yeah, they've been great. The second question, what is the discussion taking place regarding low water levels at Lake Mead and Lake Powell out west? I'm sorry, I don't know anything about that. Yeah, I know there's some people within our department who are working on water issues. There's quite a few, but I really have no idea there.
So those reservoirs right now are extremely low compared to where they have historically been because there's been an extended drought out west. Yeah, so I guess perhaps the second part of the question as to whether there's a system in place when water levels get too low to run generators, if you had any knowledge of that, or if it's prompting any thinking for you.
I haven't done a lot of thinking about that. Sorry, don't want to give an answer.
Any other questions? Well, I would like to thank you. Oh, wait, here we have another one. Okay, or maybe some explanation. With increasing demand for electric power, including the increasing spatial distribution that comes with that, what are the capacity needs and implications on sustainability, for example, in sectors like copper mining?
Sure. So we talked a little bit about increasing demand, and it'll actually change the shape of the demand curve. And if we do it right, and most of the charging for EVs comes at nighttime, they'll actually serve to flatten out the demand curve a little bit. Might actually be an advantage. And lots of people are thinking about, in aggregate, electric vehicles and the batteries within them serving as a kind of crowdsourced storage for buildings and even for the grid. So we could turn that into an advantage for sure. We're talking about the spatial distribution and all the electric vehicles floating around, serving as mobile storage. As far as copper mining and needs and sustainability, that's not something I've thought deeply about. I don't think I want to comment on that. And then David asks, will the results from your grant become available to the public? Yeah, absolutely. It's publicly funded. Department of Energy will be publishing as much as we can from that, and everything will be publicly available. Absolutely.
All right. Well, and a question about whether carrot sticks or both in spurring changes in consumer behavior.
I almost brought that up, but that's like a big can of worms. So far, it's only been the carrots angle, at least in America, where they're incentivizing people to change their behavior, and whether they do or not is up to them. There's cost implications for them. You can significantly change your electricity bill in California if you time your behavior rate. So far, there haven't been any sticks that I'm aware of. So sticks like there's things being talked about in Europe that if they notice that your thermostat is above a certain point at a certain time of the day, there might be fines associated with it. I think that's un-American and not likely to do very well in this country. But yeah, we'll see.
All right, well, thank you again, Jordan, and I want to thank everybody who was able to join us here over this lunchtime hour. I'll put a plug. Our next CONNEXT seminar is going to be in November, and that will be taking us into the transportation sector. So that'll be November the 16th at noon. Dr. Andre Carrel will be sharing some of his research where he's trying to probe directly at traveler behavior and how that can feed back into thinking about transit system operations. So getting a little bit at those thorny social behavior aspects that are tied into all of these challenging engineering problems. So I hope we'll be able to see you all then.